Hi everyone, this is Yogavalli, Assistant Professor from PG and Research Department of Mathematics in Arinarana College of Arts and Science, Krishnagiri. Now we are going to discuss about ring theory. First of all, the definition of ring. We know already what is group. A group is an algebraic structure with one binary operations. Example z comma plus g comma star. But a ring is an algebraic structure with two binary operations r comma plus comma dot. In a group there is only one operation, but in a ring there is two operations, addition and multiplication. Not only addition and multiplication, we use any operations. Okay, we will go definition of ring. A non-empty set R is said to be an associative ring if in R there are defined two operations denoted by addition and multiplication respectively, such that for all a comma b comma c in R, where the non-empty set R comma plus is an abelian group. What is abelian? The non-empty set are satisfying closure, associative, identity, inverse and commutative under addition. Then the non-empty set R is said to be abelian group. First, the closure property. A plus b is in R, associative. A plus b plus c equal to a plus b plus c. Identity. There is an element 0 in R such that a plus 0 equal to a for every a in R, where 0 is the additive identity. Next, inverse. There exists an element minus a in R such that a plus minus a equal to 0, where a is the element of R and minus a is the inverse of R. Inverse property, a plus a inverse equal to e. So, the non-empty set or satisfying inverse property under addition. Therefore, or satisfying the above 5 condition, then we say that R comma plus is an abelian group under addition. Next, R comma dot is semigroup. R comma dot satisfying closure and associative under multiplication. Closure, a dot b is in R. Associative, a dot b dot c equal to a dot b dot c. Next, the non-empty set R also satisfied two distributive laws, left distributive law and right distributive law. Left distributive law, a dot b plus c equal to a dot b plus a dot c and b plus c dot a equal to b dot a plus c dot a. The non-empty set or satisfying left distributive law and right distributive law. The set or satisfying these 9 conditions, then we say that the set R comma plus comma dot is said to be ring. The property 1 to 5 says that R is an abelian group under the operation addition, that is R comma plus is abelian group, and the properties 6 to 7 says that R is a semigroup under multiplication, which implies R comma dot is semigroup. Therefore, R comma plus comma dot is ring. Whenever we speak of ring, it will be understood we mean associative ring. What is non-associative ring? That is the ring. The ring does not satisfy the property 7 maybe fails, then the ring is said to be non-associative ring. For example, set of all integers z comma plus comma dot is a ring. Let us check. Z comma plus is an abelian group. Yes. Closure satisfying, associative also satisfying, identity. What is the additive identity? E equal to 0. Inverse of additive, a equal to a inverse also satisfied. Commutative property under addition. Next, z comma dot is a semigroup. Semigroup means only two properties must be satisfied. What is the properties? Closure and associative. Let's take two integers. The multiplication of integers also belongs to in set of all integers. That is, closure property is satisfied. Next, associative. Multiplication is associative. Therefore, a set of all integers also satisfied left distributive law and right distributive law. Therefore, z comma plus comma dot satisfying the 9 properties. Hence, z comma plus comma dot is said to be ring. Next we go types of ring. Ring with unit element. If there is an element 1 in R such that A dot 1 equal to 1 dot A equal to A for every A in R, then R comma plus comma dot is said to be unit ring. First of all, the set R is ring. Next, the multiplicative identity 1 belongs to R, then the ring is said to be ring with unit element. Next, commutative ring. If the multiplication of R is such that A dot B equal to B dot A for every A comma B in R, then we call R is a commutative ring. The ring R satisfying commutative property under multiplication, then the ring is said to be commutative ring. Example, Z is the set of integers positive and negative numbers, and 0 also belongs to in set of all integers, where plus is the usual addition and dot is the usual multiplication of integers. Z comma plus comma dot is a commutative ring with unit element. Yes, 1 belongs to set of all integers. Multiplicative identity belongs to in set of all integers. Next, 2z is the set of even integers under the usual operations of addition and multiplication. Set of all even integers is a ring. Set of all even integers satisfying multiplicative commutative property. Therefore, 2z is a commutative ring, but set of all even integers has no multiplicative identity. 1 does not belongs to 2z. Therefore, 2z is commutative ring but has no unit element. Next, set of all rational numbers under the usual addition and multiplication of rational numbers. Q is commutative ring and with the unit element. Q satisfying multiplicative commutative property, and 1 belongs to set of all rational numbers. Therefore, Q is a commutative ring with unit element. Next, zero divisor. What is zero divisor? If in R is a commutative ring, then A not equal to 0, A belongs to R is said to be a zero divisor. If there exists AB belongs to R but B not equal to 0, such that AB equal to 0. That is, if A not equal to 0 and B not equal to 0, which implies AB equal to 0, then A is said to be 0 divisor element. Then the ring is said to be 0 divisor. Next, integral domain. A commutative ring is an integral domain if it has no 0 divisor. We know what is 0 divisor. A not equal to 0, B not equal to 0, then AB equal to 0. No 0 divisor means A not equal to 0 and B not equal to 0, which implies AB not equal to 0, or AB equal to 0, which implies A equal to 0 or B equal to 0. Then the ring is said to be has no 0 divisor. A commutative ring plus has no 0 divisor, then the ring is said to be integral domain. Example, the ring of integers z comma plus comma dot, it is an example of integral domain. For example, A equal to 1 and B equal to 2. 1 not equal to 0 and 2 not equal to 0. AB 1 into 2 equal to 2, also not equal to 0. AB not equal to 0, have no 0 divisor. Therefore, set of all integers is the example of integral domain. Next, division ring. A ring is said to be a division ring if it is every non-zero element as a multiplicative ring. First of all, R is a ring. Next, every non-zero element have a multiplicative inverse, then the ring is said to be division ring. Non-zero element means except 0. No, the unit element under multiplication will be written as 1 and the inverse of an element A under multiplication will be denoted by A inverse. Finally, the definition of field. What is field? A commutative division ring is called a field. Field is, it should be a commutative ring if every non-zero element has multiplicative inverse, that is R comma dot is inverse must exist. Okay, example, set of all rational numbers is a field. Set of all complex numbers is the example of field. Set of all integers modulo 7 is the example of field. Rational numbers, complex numbers, set of all integers modulo 7, all are examples of field. Thanks for watching.